All right, guys, now that we've talked a little bit about work, I want to take a moment and talk about springs, and specifically then look at the work done by springs. And springs, as we'll see, calculating the work done by a spring is a little bit tricky. But before we get into the work done by springs, I want to talk a little bit about spring forces. So we'll begin by thinking about spring forces. So let's imagine I've got, I don't know, maybe a spring hanging from a ceiling for some reason. So here's the ceiling right here. Ceiling. And I've got a spring hanging from that ceiling. And now what I'm going to do is I'm going to imagine that I pull down. I grab a hold of the spring and I pull down with some applied force. And if I do that, the spring is going to stretch. But what's interesting is when the spring stretches, then there's going to be a force backward, which is, I'm going to call it F sub SP. That's for the spring force. And what's interesting about the spring force, and if you've ever, as I'm sure you have, played with a spring or a rubber band or anything that's stretchy or elastic, there's a relationship between the force that the spring exerts and how far it is stretched. So the distance, what I'll call delta x from equilibrium. And just so we're clear about what equilibrium is, that's sort of like the resting length. The resting length of the spring. So if the spring is just hanging there, it has a resting length. And if I then pull it down some delta x, the spring is going to pull back in the opposite direction with some force. Another way we could think about it is I could imagine having like a horizontal spring like this. And if this point right here, if this is the equilibrium point, and I call that x equals 0, and then I go ahead and I pull the spring out. Imagine I'm pulling, and I pull the spring out to a new position out here. So this will be some new position x. There's then been a delta x here. And if there's a delta x, then we're going to get a force backwards from the spring in the opposite direction. I hope that makes sense. So it can be either in a vertical situation or a horizontal situation. But either way, I want to get back to this idea that the force is related to the distance stretched. And I want to come up with a way of calculating the spring force. So F spring. And it turns out there's only two things that matter. The first one I already mentioned. That's the distance stretched, delta x from equilibrium. And the other thing is we need to somehow measure how stretchy the spring is. Some springs are very weak. You apply a little bit of force and they stretch a lot. And some springs are very, very strong and it's really hard to stretch them. They're not very stretchy. So we need a constant here, which is K. And K is known as the spring constant. And this is different for different springs. Spring constant. And you can think of it as a measurement of how strong the spring is. If the K value is large, that means it's a very strong spring. If the K value is weak, or a small number, that would mean that the spring is weak. The unit here, just to shed some light on this, the unit is the Newton per meter. So what that means, if we think about it, is if you had a K value here of 1 Newton per meter, that would mean if you exerted, or if you pulled on the spring with 1 Newton, 1 measly Newton of force, it would stretch an entire meter. So a 1 Newton meter K value would be really, really small. So you can often get, hundreds or thousands or hundreds of thousands of Newton meters for spring constants. And then the last thing we sometimes put up front is a negative sign. And the negative sign, so maybe let's just break this down. K is the spring constant in Newton meters. Delta x, we already know what that is. That's the distance from equilibrium. And the negative here just tells me that the direction is opposite. So F is opposite from delta x. So if I pull the spring to the right, the force is to the left. If I were to compress the spring to the left, the force would be to the right. The direction is opposite direction. So now we have an equation, and this is an equation that has a name. Historically, this is called Hooke's law, this equation right here. And allows us to calculate the force a spring exerts. So this is known as Hooke's law. Oh. And that gives us the spring force. So now that we know a little bit about springs, I want to talk about the work done by springs. So let's move on down here and talk about the work done by springs. Work done by springs. And I think you can see here maybe that it's going to be a little bit tricky. And the reason is we remember that our equation for work is work equals, I'll do this in blue, work equals force times distance. I'm for right now, I'm going to we know that there's a cosine theta here, but for right now we can sort of ignore that, as we'll see. But the tricky bit is that what we have in a spring is that, of course, the force, F, the force depends on the distance, right? As you stretch the spring more and more and more, as D gets bigger and bigger and bigger, F changes. F gets bigger and bigger and bigger. So there's a kind of an issue of like, if the force is constantly changing, what do you plug in for F? I hope that makes sense, right? The whole point of Hooke's law, the whole point here is that the force is not constant. Maybe I'll write that out. So the force changes with the distance. And if that's the case, that means that this F is changing as D changes. So that makes this a little bit tricky. I'm not going to go ahead and derive this equation for you, but it turns out that there is a way of dealing with this situation. And maybe the simplest way to think about it is what we could do is we could say that the work is going to be the average force times the distance. And the way to calculate the average force is just going to be, I'm going to take the initial force and the final force, and I'm going to divide by 2. And that's going to give me an equation that's going to look like this. The work done by a spring is going to equal 1/2 k times x squared. Again, I haven't derived that for you. I'm not going to spend the time right now going into that in any great detail, but this is now an equation that we can use for calculating the work done by a spring. So this is the work done by a spring. And just to be clear here, maybe I should have written this actually. I think I'm going to just change this slightly. I'm going to write that as delta x. Remember, that's our distance from equilibrium. We know what that is. That's the distance stretched from equilibrium. And again, k is that spring constant. It's the same k as we had up here. Same k, spring constant. And now this equation will allow us to calculate the work done by a spring. I hope that makes sense. You'll have an opportunity to practice using both of these equations, both this Hooke's law equation up here and this work done by a spring equation on the next problem set.